Hi everyone. Okay, today we're going to learn about operational amplifier, or also known as op-amp. So op-amp, as the name implies, is to do operations. Okay, so here, for example, we want to do mathematical operations. This op-amp can also amplify our voltage. Okay, it is a basic component to build analog circuits with very high input impedance and high gain for differential amplifier. So it has either open loop or closed loop. For this class, we're going to cover a few for open loop and closed loop. For open loop is focused on non-linear applications and closed loop focus on linear applications. Here is a op-amp. It has two inputs and also one output. The input is labeled as positive or negative or plus minus. So here, if the connection connected to the plus or positive part, this is called as non-inverting input. While if the input is connected to the negative part of the op-amp, this is called as inverting input. Okay, we label it as V plus and V minus. To use this op-amp, we need to have a voltage supply to it. Usually is plus VCC and minus VCC. It depends on the connection that is going to be used in your application. However, the output is only one. Ideally, this is how the op-amp looks like. It has inverting input connected to negative part, non-inverting input connected to positive part. The current flow into the op-amp is called as or labeled as I minus or I plus. If the current goes to the negative part, we label it as I minus. While if the current is connected or flow to the positive part, we label it as I plus. So we must have a voltage supply to use or to operate this op-amp. For the ideal op-amp characteristic, it will be limited by the voltage supply, either V plus positive VCC or negative VCC. Over here is called saturation. However, the op-amp can amplify or operate in a linear region in between plus minus VCC. So in this linear region, the op-amp can do amplification. The DC offset parameter for the op-amp is caused by few. So this offset means it is off from what we set. Okay. For example, we set input voltage, but it gives error or offset value. So we call it as input offset voltage. While for the offset at the output, we also call it as output offset voltage, which due to input offset current. It means that the current that we set is off from what we set. That is the term. There is also total offset voltage. This is due to input offset voltage and also input offset current. Input bias current also can cause this DC offset parameter. So for input offset voltage, the label is usually found to be VIO, is the voltage between two input terminals to obtain Vout equals to 0. Ideally, Vout is equal to 0 only when Vin is grounded. In reality, the input terminals are connected with different DC potential . The value of output offset voltage can be calculated as the following equation. Or it caused by the difference between DC bias input currents for the same applied input. Input offset current can be found as I plus minus I minus. So I plus is connected to non-inverting input and I minus is at the inverting input of the op-amp. For input bias current, IB, usually found as I plus plus I minus divided with 2. So this current that passes through the inputs, usually there is no current flow at the input. So this is the ideal case. However, in reality, there is tiny amount of current that flows into both inputs. So usually the range is between femtoampere to microampere. For example, if we use high-speed op-amp, the input bias current usually found as microampere. If we use general purpose op-amp, the input bias current found to be in nanoampere. And if we want to use it in high precision, or we use high precision op-amp, usually the current amount is femtoampere. However, IB is very small, where we can neglect the effect of IB except for application which we want to require precise current value. This is general purpose op-amp LM741. Here is the datasheet. So we can see here there is a internal block diagram. In a simplest model, it have 8 pins. You can see there is number 1 until number 8. So number 1 or pin 1 is offset null. So how do we read this is as input 1, or on the right is the input 1. So for this op-amp, we can see there is a curve, okay, on the physical of the op-amp. There is a curve on the physical. So here on the left of the curve is the first pin. Okay, there is a black dot over here to indicate this is pin number 1. So we read it counterclockwise. So input inverting is at pin number 2. Input non-inverting at pin number 3. Okay, here we have VEE and VCC. So in the previous slide, I have mentioned about the voltage supply for the op-amp. So here, for this LM741, the voltage supply is labeled as VCC and VEE, pin number 7 and pin number 4. In order to use this op-amp, we must make sure that pin number 4 and pin number 7 are connected to voltage supply. Okay? The output for this op-amp is at pin number 6. So on the right side is the physical view for the op-amp. Example, if this is two different packaging type, or it is used for different mounting style. Okay, the first one is DIP, or the term is dual inline package. So this is for through-hole PCB. If you see your PCB, if there is a hole that solder the components, okay, that means it used the through-hole components. Or there is also SOP type for this op-amp, small outline package, or this is for surface mount device. This is the schematic diagram for the LM741. Here we can see there is only two inputs, okay, for the op-amp to operate, only two inputs, and only one output with voltage supply VCC and VEE. However, actually, inside the LM741, there is BJT with more than one transistor. Okay, here we have from Q1, it labeled as Q1 up to Q24. It means for this LM741, in reality you have about 24 transistors. Okay, so not only one, we learn in BJT chapter, we cover only one BJT or one stage BJT, and then in multi-stage amplifier, we learn about two BJTs in a circuit, and then for this op-amp, actually we have more than that. Okay, so here we have 24 transistors. So for the voltage supply for this LM741 is plus minus 18 volt. Okay, this can be found in the datasheet. So different company will provide different supply voltage for the op-amp. The advantage for op-amp as listed below. For the linear application, in this course, we will cover 5 linear application: inverting amplifier, non-inverting amplifier, voltage follower, summing amplifier, and also difference amplifier. This is example of the op-amp which are used for linear applications. We draw our op-amp in a triangle shape and label it with 2 inputs and 1 output. For example, here we have inverting op-amp. We can find the gain equals to as listed in the box here. Non-inverting op-amp, differential op-amp, summing op-amp, and also voltage follower. So for inverting op-amp is because the input is connected at inverting input of the op-amp. So we want the op-amp to invert our input. That's why we get the output equals to minus Vout. For non-inverting op-amp, we connect the input to positive input of the op-amp. For differential op-amp, we want to differentiate between two inputs. So we connect two inputs to both of the op-amp inputs. We have V1 and V2 in this example. For summing op-amp, we want to sum, or plus the voltage at one part of the op-amp. So in this example, the summing of V1, V2, and V3 is at inverting input. Okay, that's why the output here is labeled as minus Vout. We also can connect the input at the positive input of the op-amp. And then the output will be positive Vout. Next is voltage follower. Voltage follower means the gain is 1. So why we didn't want to amplify the signal, but we want to prevent it from such as reverse current. So we can use op-amp to protect our input circuit with our output so that it won't destroy or break or damage the input of the input circuit. So let's try to do inverting op-amp, how the gain is minus RF divided with Rin. Firstly, we label the current and the voltage for this diagram. So I label this as the input is at the inverting part. So here is In, and then at the current at RF is labeled as IF. And we also have I minus, which the current that goes into the inverting input of the op-amp, and also the current that goes to the non-inverting input of the op-amp. Also, we have at the negative here, we have V minus, and also over here we have V positive, V plus. So for our case, we want to do a general purpose operational amplifier. Therefore, we can take a ideal case for the op-amp, which are I minus equals to 0, I plus equals to 0, V minus equals to V plus. Okay, this is listed in the earlier slide. So how to do the gain? We can take KCL at the input part. So here KCL at first node here on the top, we have In equals to IF. So I in is voltage divided with resistor. Voltage divided with resistance. So we have V in minus V minus divided with R in equals to V minus minus V out divided with RF. Since V minus is equals to 0, therefore our equation will be V in over R in equals to minus V out. So our A gain V out divided with V in equals to minus RF divided with R in. Okay, or you want to take I in equals to IF. So we want to take the current is from the top voltage divided with the earliest voltage. So we have V minus minus V in divided with R in equals to V out minus V minus divided with RF. So minus V in over R in equals to V out over RF. Therefore, the gain is V out divided with V in equals to minus RF divided with R in. So you can choose to use either V in minus V out over R in or V minus minus V in divided with R in. Both will give you the same gain. Okay, but make sure if you take V in minus V minus, and make sure for IF you also take from V minus to V out. Okay, make sure I in and IF you take the same direction or the same way you read the voltage. Okay, so for example here, I in, you take V in minus V minus divided with R in. And then you want to take IF equals to V out minus V minus divided with RF. So this one is not the same. So you will get different answer. Okay, so make sure you be careful with how you read the voltage for the resistor. Okay. Next we have non-inverting op-amp. So non-inverting means the input is connected to the non-inverting part of the op-amp. So here you have R in and RF. So just I put label I in, okay, IF label here, I in over here. So here we know that the current that goes into the op-amp, I plus and I minus. So I plus equals to I minus equals to 0. And then we have another parameters, V plus and V minus. So V plus equals to V minus. Let's take the KCL for the bottom part. We have here is I in equals to IF. So just do the KCL and Ohm's law. V minus so V minus, here you can see the V in is equals to V plus. Therefore, V plus is equals to V minus. Okay, then we replace it in our equation. 0 minus V in divided with R in equals to V in minus V out over RF. So V out, we take V out to the left side, V in to the right side. Okay. Therefore, if we want to take simplify the equation, it will be V in bracket 1 over RF plus 1 over R in. Therefore, V out over V in is again will be equals to RF 1 over RF plus 1 over R in equals to 1 plus RF over R in. Okay? That's why you get here same with equation. Next, we have differential op-amp. Okay, so here I minus and here is I plus. So here is V minus and V plus. For our case, we take ideal case. Ideal case, I plus equals to I minus equals to 0 and V plus equals to V minus. We take the first KCL first. So here I label as I1 and I2. So KCL at node V minus I1 equals to I2 plus I minus. Okay, since I minus is 0, therefore I1 equals to I2. So we take the Ohm's law for this current. We have V1 minus V minus divide with R in equals to I2 is V minus minus V out divide with RF. Therefore, here we have V1 over R in equals to minus V out over RF. So this is first equation. And then we take the KCL at node V plus. We have here I3, I4. So I3 equals to I plus plus I4 equals to I4. So the Ohm's law for I3 is V2 minus V plus divide with R in, and Ohm's law for I4 V plus minus V out. Okay, V out is connected to ground. Therefore, V plus minus 0 divide with RF. So here we will get equals to 0. Then V plus also 0. Therefore, V2 over Rin equals to 0. So this is equation number 2. So we differentiate between both equation, 1 minus 2. So we have here V1 minus V2 over Rin equals to minus V out over Rf minus 0. So equals to minus V out over Rf. Here we have V out. Okay, we want to take the value V out equals to, bring Rf to the another side. So we have Rf over Rin V2 minus V1. Okay. Alright. Next is summing op-amp. So here the summing happen at the inverting part of the op-amp. So this is inverting summing op-amp. Okay, just label I1, I2, I3, I4. So we have ideal case, I plus equals to I minus equals to 0, V plus equals to V minus. So here you can see the non-inverting part of the op-amp is connected to the ground. So here we have V plus, right? Therefore, V plus here equals to ground. V plus equals to 0. Okay, let's do the KCL at the top part of the op-amp. So we have I1 plus I2 plus I3 equals to I4. So I1, just put the KCL for I1. V1 minus V minus R, divide with R plus so V minus equals to 0. So you have V1 over R1 plus V2 over R2 plus V3 over R3 plus minus V out, equals to minus V out over Rf. So if you want to know how much is V out, rearrange the equation. V out bring Rf to the other side. So V out equals to minus Rf V1 over R1 plus V2 over R2 plus V3 over R3. Okay, that's it. Next we have unity voltage follower. Okay, so how do we do this? Firstly, we know that the current that goes to the input of the op-amp is I plus and I minus. Also there is a voltage across the input. So we take KCL. Before we take KCL, we write down the ideal case for op-amp or general purpose op-amp. I plus equals to I minus equals to 0. V plus equals to V minus. Okay, we have this. Therefore, we need to determine how much is V in. So since in the circuit, V minus is connected to V out. So V minus is connected to V out. Okay, and also V minus is equals to V plus. Therefore, V plus is also equals to V out. And since V in is equals to V plus, therefore V in is equals to V out. Okay, if you want to find again, A equals to V out over V in. V out over V in, we get 1. That's it. Here is example. If we have summing, okay, summing at the non-inverting of the op-amp input. Okay, so we know that we need to sum or add V1 plus V2 plus V3. And then we get the output. Okay, so this is same with on the previous, which is inverting summing. Okay, this is inverting summing, but the concept is same with this op-amp. Okay, so firstly what we can do is we label our current I1, I2, I3. And then here we have V minus, here V plus, here I minus, here I plus. So we take ideal case for op-amp, I minus equals to I plus, V minus equals to V plus equals to 0. Okay, so for this, we need to write KCL at node V minus and also at node V plus. Okay. Then the question asks to derive mathematical equation of V out. Okay, in terms of V1, V2, V3 and resistances. Here means you don't need to replace the R value or V value. You just put R1, R2 or R3, RF1, RF2 in your answer. Okay, and then for question number 2, it gives you the value for V1, V2 and V out, but you need to determine how much is V3. Okay, in question number 2, you need to replace the R1, R2, R3, RF2, RF1, V1, V2, V out, and then find V3. Okay, I have write the answer over here. You can check and let me know. For question number 1, you need to just derive the equation. So here, I write the answer over here. And for second question, you need to determine how much V3 values with the given voltages values. Okay, so you just replace all of the voltage and resistors value into the equation and find how much is the V3 value. So another example is also summing amplifier. So here is the summing inverting. The input is sine omega t, oh this is sine omega t volt, and V2 is 5 volt. So firstly, you need to label the I minus, I plus, V minus, and V plus. So here, I minus equals to I plus equals to 0. V minus equals to V plus. So here V plus is connect to the ground, so it is equals to 0. Same concept, you need to define the KCL, and then you need to derive the mathematical equation. Okay, so you just need to find the equation for V out. And then draw the output signal for V out. So I have give you the answer. Okay, so this one, this one is not linear op-amp. Okay, this is non-linear op-amp. However, the concept how you want to do the KCL, how you want to replace the I plus I minus equals to 0 and V plus equals to V minus can also can be applied to this circuit. Okay. Okay, so for next is non-linear application.